Hi, and welcome back to Allen High School's discussion of electrochemistry at the AP/IB/HL level. Now, I'm going to just kind of skip a couple of things in the notes for the sake of time. We just did one of these, but this is different. Be really careful with this, but I want you to work this. So I'm going to expect you to work this when I check your notes. We did this way back in Chapter 1. It's here for review. I'm going to bypass it and move on. I'll be doing a lot of assigning of redox numbers, so I think you'll get this as we go. So I'm going to start right here at You Do It 16. First off, before we answer these questions, we have to assign oxidation numbers. Pure substances all by themselves are 0. Oxygen is -2. Be really careful, because when oxygen's with hydrogen or a group 1 metal or maybe a group 2 metal, every once in a while you'll see the peroxide. So be really careful with that. You might want to assign the positive one first and make sure that you're still at oxygen -2, which is of course the most common. Now, hydrogen went from 0 to +1. It became less negative, so it lost electrons. So hydrogen was oxidized, which makes hydrogen the reducing agent. Oxygen is reduced, which makes O2 my oxidizing agent. Okay, let's assign oxidation numbers. When oxygen's in a ternary, it's always going to be -2. Potassium's +1. If you did your balancing of your calculation, you should get nitrogen at +5. I have -6 from the oxygens. +1 means I'm now at a -5 that I have to balance with that. All right, -2, +1, +4, and 0. Okay. The potassium stayed the same. The nitrogen went from +5 to +4. That is more negative, meaning we gave it electrons. Reduction is gain, oil rig. So I'm going to put the nitrogen with the 5+ oxidation number. Be very specific. You can't just say nitrogen because there's 2 nitrogens in the reaction, and you've got to prove your case thoroughly. Now, whatever is reduced is also the oxidizing agent, so that puts nitrogen there as well. Oxygen, at least some of it, was oxidized. So the oxygen with a -2 oxidation state was oxidized, and that makes that the reducing agent. Now, I want to do this next one. It's a little tricky. You have 2 nitrogens in here, and in this case, really the only way I would be able to do this, separate this into the polyatomic ions, and then do the oxidation numbers. So I have 1 nitrogen, I have 2 oxygens, and they're at -2. So 2 oxygens are -2, and I have a leftover of a -1 charge. Okay, so that, you know what, I messed this up. That's a +3. I just caught that. Okay, that's a +3 back there. So that makes this nitrogen equal to a +3. Right? And then this nitrogen, I have 4 hydrogens. They're each +1. The only time hydrogen's -1 is when it's all by itself with a metal as a hydride. So plus my nitrogen is equal to +1 left over. Okay, so that makes my nitrogen +5 in this case. Excuse me, Dina. I can't do math. All right, so I've got nitrogen would equal, so 4 positives, subtract that over there, it would be -3. Okay, so the nitrogen is this nitrogen is -3, this nitrogen's +3. So the nitrogen that is -3 went to 0. So the nitrogen in ammonia went to 0, and the nitrogen in nitrate was reduced. Okay, so that makes this and this. Okay, so hopefully you're getting that picture. Now, let's do some balancing of half reactions. I just want to do one quick one in here. Here is in words what we're going to do. I think it's a lot easier just to see it worked through for you. And we've done some already. I've already gotten a start on this. Step 1 is to write down all your oxidation numbers. So I have +1, -2, and 0. -2 plus 4, -2 plus 1. Now, what I'm going to do is pluck out different species just to focus on them. I'm not breaking bonds. I'm just focusing on them. The sulfur that had an oxidation number of -2 went to sulfur with a 4+ oxidation number. Okay, so that sulfur was oxidized. It lost 6 electrons. Now we're balancing electrons and also charge. What I would recommend doing, because I've messed up before, double check that your charge is equal on both sides. You might catch yourself putting the electrons on the incorrect side if you do that. 6 negatives plus 4 positives is -2, and I have -2 on the other side. All right, now let's look at the oxygen. O2 went to O2 negative. Now, because of that 2 here, I'm going to go ahead and put a 2 here. In other words, I have to have a multiple of 2 be reduced in this case. It's at least 2. It could be 4, it could be 6, but it's not going to be 3 and it's not going to be 5. Okay? So that's plus 4 electrons, 2 per oxygen. Now, I have to balance my electrons. My charge is 4 negatives on this side, 4 negatives on that side. Now I've got to balance electrons. I'm going to do the least common multiple of 6 and 4, and that's 12. So I'm going to multiply that by 2 and this by 3. Okay? Now, when I do that, I'm going to rewrite them down here. I have 2s2 negatives going to 2s4 plus 12 electrons, and 12 electrons plus 3 O2 going to 6 O2 negatives. Now, we have here 4 coefficients that we can use. 1, 2, 3, 4. You're going to be able to use at least 3 of them. And once you have 3 of them in the equation, don't worry about the 4th, all right? So I asked questions of myself. I said, is this the only sulfur on the left-hand side? Yes. Is all of it oxidized or reduced? In this case, oxidized. The answer is yes. Is this the only place sulfur shows up? Yes, I can put that 2 there. So I've got that 2 done and that 2 done. O2, I need 3 of them. Is this the only place it shows up on the left-hand side? Yes. Was all of it changed? No. That is the total oxygens that changed. I'm not going to worry about it. I'm going to go back to normal balancing. Once you get 3 in here, just go back to normal balancing techniques. I've got 4 hydrogens here, so I need 4 hydrogens there. And there's my 2 plus 4 is my 6 oxygens and 6 oxygens. So I'm done. All right. Now, in the next video, we'll see what we do in an acidic solution. So until then, this is signing off.